And it's my real pleasure to introduce Dr. Queenie Chan as our keynote speaker this evening. I've heard Queenie speak before, and I think we're in for a real treat tonight. Queenie is a planetary scientist. Her work involves the analysis of chemical and organic contents of meteorites and cometary material, and her research has been really quite fascinating. She's currently a lecturer at Royal Holloway and a visiting fellow at the Open University. And prior to that, she was a postdoctoral fellow at NASA at the Johnson Space Center, which gave her an opportunity to do some really fascinating research. And just a quick look through her publications, a few things jumped out at me as really fascinating. One of which was looking at chlorine isotopes in lunar materials, and another one looking at fluid inclusions in meteorites, looking at some of the earliest aquatic chemistry from the solar system. So Queenie has done some really fascinating research. Her PhD is from Imperial College. And tonight she's going to tell us how water and life's simple building blocks were delivered to the early Earth. So Queenie, thank you very much for speaking to us tonight, and over to you.
Hello, thank you for the introduction, and it's really a pleasure to be here talking with you about something that I love, my research and my recent results of some investigation of some quite interesting meteorites. So let me now try to share with you with my screen. I hope you can all see the screen instead of me talking in front of you. That's great, thank you.
That's good.
So yeah, that's great. So what I'm going to do today is talk to you about shooting star, and that's not me. That's the actual shooting star meteorites. And during the talk, I will hope to interact with you a little bit too. So I will ask a few questions, and you could put down your answers in the chat box. So usually it's just a quick answer, yes or no, left or right, that sort of thing. So it'll be hopefully quick. So the chat box should be down at the bottom of your screen where it says chat. So you could put your answers there, and you could also put your questions there. I won't be able to answer the questions during the talk, but I'll go over them at the end of the talk. So feel free to pop down anything over there. Right, so let's start. So whenever we heard stories about asteroids striking Earth, it's always bad. It's always something that's coming quite big, and it's going to hit the Earth, and it's going to cause Armageddon, something like that. It's always asteroid. It's always something scary, is because they're trying to make the news. And story about the dinosaurs and how to kill the dinosaurs. It's always asteroid. It's always bad. Armageddonish. So today, don't worry, because I'm going to share with you how I crushed them and take the revenge for the poor dinosaurs. I'm a meteoriticist. I study meteorites. I crush them, powder them, extract organic materials from them, and study what organic material are hosted within them to help us understand the origin of life. And other than meteorites, I also am involved in space missions. So if you've heard maybe recently a space mission that just came back to the Earth carrying rocks from an asteroid, the mission called Hayabusa 2 of JAXA. It is a sample return mission. So I will get to analyze the samples returned from a space mission like that. Very exciting. And but mainly meteorites and dust particle from space. So before I go into those details, maybe we'll go through some quick terminology, because I would talk about them throughout my talk. Comets, we're talking about a small body, small, still bigger than hand specimen of meteorite, but small enough compared to a planet. A small body made up of ice. Usually we consider them to come from further away from us in the solar system, outer solar system, so colder material comets. We've got asteroids, a large rocky body in space, usually reside in between, within the asteroidal belt. Meteoroids, a small rock body again. So when asteroids break up into smaller pieces, we call them meteoroids. And when meteorites enter the Earth, and when it's got hit up during the atmospheric entry, it hits up, lights up, and become a fireball. And at that point, we call them a fireball, or we call them a meteor, a shooting star, making an entry to the Earth when it also explodes. And when that happens, we call them a bolide. And finally, after all these, if it still managed to arrive to the surface of Earth, where we could collect them, we could look at them, we could lick them, we could do whatever we want, that is a piece of meteorite. So when we talk about studying meteorite, we're talking about hand specimen, rock specimen that we could touch, we could analyze them. So this is a quick video that shows you how a meteoroid, which was from a larger piece, which was from an asteroid, breaks apart when it heats up during the atmospheric entry. It heats up, it melts and breaks into pieces, and as you can see here, finally it becomes a bolide. And it is a diagram that's simulated by I think it was by NASA, with the data from Chelyabinsk meteorite that fell to Earth a couple of years back in Russia. You might recall that we've heard the loud bang, and a lot of people collected meteorites coming from that Chelyabinsk meteorite. So at the end of that atmosphere entry, after most of the material got vaporized, after it breaks up into small pieces, some part of it managed to arrive to the surface of the Earth, becomes meteorite, and we could collect them and study them. So here is a quick question to you all to kickstart the interaction. How much do you guess as in the weight of extraterrestrial? There is a typo right there. Extraterrestrial material for each year. Is a weight of 10 elephants? Is a weight of 100 elephants? Or is it a weight equivalent to 10,000 elephants? So I'm going to look at the chat box and see if there's any 10,000. Yeah, that's great. 100 elephants. I'm going to wait for a couple of more seconds for a few more interactions. So no one guessed 10. This number is too small. Right, I think the majority is about, oh, there's an innovative answer, 1,000. Something in between the two. Tricky question, isn't it? Right, so the answer is 10,000. It's quite a lot. Who wouldn't guess the largest number for a question like this, right? Go for the largest number. So we have equivalent to the weight of 10,000 elephants of extraterrestrial material fall to the Earth each year. That includes meteorite, larger pieces of rock that fell and collected on the Earth's surface, and including dust particles, very, very small dust particle. And as a matter of fact, the majority of extraterrestrial material arriving on the surface of Earth is actually the smallest particle. Combined mass is more than what we could get for larger material like meteorites. But all combined, about 40,000 tons of material arriving on the Earth's surface. So we've got meteorite that arriving on the Earth's surface, and we've got meteorite that got classified into what we call a fall meteorite, which means that it's been observed as a fall event. So people saw that meteorite arriving with a fireball event and went to the locality, collected, and that is a meteorite fall. If we find a meteorite out of nowhere, like in Antarctica, we don't know when it was fell to the Earth's surface, we just found it and know this is a meteorite, that is a find meteorite. So here on this image here, on this slide here, you're looking at a fall and a find. So let's give it a guess. Which one is a fall? Which one is a find? And again, put it in the chat box. Just take a guess and see which one do you think is a find meteorite and which one is a fall meteorite. So on the left or on the right is a fall meteorite. On the left, fall on the left. That's right. Why? How do you know that every 100% of all the answers is fall on the left? How do you all know it's all right? And that's correct. And they are the Chelyabinsk meteorite that fell to the earth a couple of years ago, as we mentioned just a couple of slides ago. And on the right is a very famous meteorite, Allen Hill 84001, that fell in 1984. So the Allen Hill is a place in Antarctica. The year of its fall is year 84, if you can see my cursor. So this number and the year and the place becomes the name of this meteorite, of Antarctica fall meteorites. Chelyabinsk is the one that we observed this entry, the majestic entry, and collect quite a bit of material from this meteorite. So as I recall, falls are meteorite with a observed fall event, and finds a meteorite collected without an observed fall event. But the majority of meteorite that are collected as finds are forms the majority of our meteoritic collection on Earth. Is 98% of all meteorite collected on Earth, and just that 2% are with observed fall event, and they're very precious because we know when they fell, and usually we go straight after it. We go to collect it right away. So compared to the find meteorites, usually they're more they're cleaner, they're collected quicker, they're not contaminated as much. A good example of that is our UK meteorite that you must have heard that fell to the earth and to the UK soil a couple of months back in the end of February. Is this Winchcom meteorite. Fell over here, a couple of pieces of material get collected right after its fall. And amazing part of it is that because it's been observed, so you can see these videos that I'm showing you, they're all from security camera, from other people's doorbell, or from a camera observing, is a network of camera observing meteorite fall. So combined effort, we've got so many footages of how this meteorite fell on Earth. We know where it came from, because from the trajectory, we kind of calculate its orbit before it arrives to the Earth's surface. So we know a lot about that, thanks to the effort of every single one of us in the UK, combined effort of that. And we collect the material straight after that. It's one of the most promptly collected material, meteorite. And it's a carbon-rich meteorite, so it's very special. I think one of the most quickly collected material was collected somewhere within a day. So it's really, really clean, really pristine. And it was found in kind of dry environment on the Wilcox family's drive. You can see the powder thing there. Some got arrived on soil. It's good that it's not going into the lake where it gets contaminated by the lake water. So most of them fell in dry environment and collected straight away. So we've got all this amazing meteorite sample for us to just study, including 4 materials. So here, a find meteorite. You find it in Antarctica. So here, Antarctica, in a white piece of land, you find one rock sitting right there. So it's very easy compared to fall meteorites, or like compared to Winchcom, where you have to search for it. In Antarctica, you also need to search for the rock, but it's comparatively easier. Maybe the contrast is a bit easier. 60%, more than 60% of meteorites are Antarctic finds, and about 30-something% are non-Antarctic finds. So majority of found meteorites coming from Antarctica. most of the reason is because they're kind of easy to look for them. They are well preserved, so that's why we wanted to go there. It's kind of dry compared to tropical environment. So less weathering, more pristine material from Antarctica. And another reason why they're so easily to be found is because when we found them, they kind of like collected in the same area. The reason for that is because when meteorite fell on the snow, because of its weight, it sank to the bottom and got carried by the ice flow. And then this pile of snow on the surface got ablated away by the katabatic wind flow. And so that chunk, that bulk of meteorite traveled along the transantarctic mountain and collected at the foot of the transantarctic mountain, got concentrated like that and exposed to the surface for us to kind of easily find them. So people take expedition every year to Antarctica by different countries. For example, in America, they've got an Enzymate team to go there to Antarctica to collect meteorite. So they've got this amazing expedition with a group of planetary scientists, mostly went to set camp in the middle of Antarctica and going on snowmobile. It's a fantastic holiday. Go on snowmobile, finding those meteorites. So what they would do is when they find a meteorite, they'll put a flag there, just so that when people need to come back to the site, that they'll come back, revisit the site. And then the next thing that they would do is to record it. So they would examine it. Is it a real, kind of real Antarctica rock? Or is it a meteorite? So they would examine it, because Antarctica has also got Earth rock. So we need to examine it to make sure that it is a meteorite or not. So first thing, to examine it, document it, bag it. So if you could see the kind of like video, it mustn't, it shouldn't be too smooth, but you can see that they wrap them up into in aluminum foil and bag it, store it, and note the place where it was found. And you can see here, this is a scale from 0 to 6 centimeter, a number of it, then they take a picture of it. So each meteorite got a unique number of that year. So we know how many meteorites we'll collect. And then people could send them to NASA, back to NASA, and store it and release it to different people, different researchers who requested them for further analysis. So this one is the biggest Antarctica meteorite, the Big Blue, this one here. And when the meteorites got collected, they got sent back to NASA by ship and keep frozen until we need to open them for study. So this is an example of how scientists at NASA slides open a rock and cut it into pieces so that different people, different researchers could study different pieces of rock of this big sample. So the Speculum is the largest Enzymate meteorite collected since 1975. It's not the heaviest because it's not a iron meteorite. It's a more rocky type of meteorite, so it's not so heavy, but it's the biggest. And here is it. I'm there, and my boss at NASA, and we're next to Big Blue. It's kind of big, and so you can see we're wearing full coverage for protective layer is to protect the meteorite from us, not to protect us from those radioactive meteorite. Not like that. It's just to control the contamination. And there is no excuse, because even when I was pregnant, this is 2018, 10 days before my Ethan was born, I was in a gown like that. So no exception. Everybody goes into the meteorite collection curation facility. We have to dress up like this to avoid terrestrial contamination. So several ways when you find, when I was saying people went to Antarctica and searched for meteorite, how do they know it's a meteorite but not an Antarctica rock or any rock? So there are several ways that we could do that. And here is the first one is the fusion crust. So you could see that on the surface, it's kind of dark, right? It's kind of like glassy dark. It's because during the atmospheric entry, the peak heating temperature could go up to 1,000 degrees Celsius. It's really high. It could quickly melt the surface of that rock. But because the atmospheric entry doesn't take really long, so when it comes down, when it's slow down or arriving the surface of the earth or closer to the surface of the earth, it's kind of cool down really quickly at the same time too. So that molten rock cool down quickly right away, form a tiny thin layer of what we call the fusion crust. Is that so its molten material got cooled down and solidified really quickly. It's usually about 2 millimeter in thickness, very thin. And we've got something called the Rockman Lips or the flow lines. So they are basically when during the atmosphere entry again, the meteorite got heated up so bad and parts and pieces of the surface of the meteorite got ablated away, got taken away during the entry. So you could see indentation like that or flow lines like that again because they got melted and pieces of it got loosened up and got taken away during the entry and form this kind of feature. So this again tells us that something has gone through that kind of atmospheric entry process. So we take that as a implication that it is a space rock. Also the special content. So this is a meteorite that's got really large crystals of what we call the olivine crystals. Next to what you could see here, those are iron. So metal right next to large crystals like this. So it's kind of special content that is usually found in some space rock. And another thing is the chondrules. So these are the circular blobs in the rock. They're amongst the first solid that got condensed and formed during the formation of our solar system. So before the formation of planet, the first solid that formed at the birth of our solar system are chondrules or CAIs, and they got trapped in meteorites. And when we find them, we know that it is meteorite. It's not coming from a planet. It's not coming from Earth. It must be somewhere else. So these are all several ways that we could use to identify meteorite. So if you happen to really find it, a meteorite, or if you happen to observe a meteorite fall, then the first thing is you would think, okay, so now it happens. What should I do now? It's a couple of things. So first is to note exactly where the direction where the fireball disappeared, and mark your own position. So when you observed it, where you were, where the fireball went. So mark down all the location, the direction. This is to help us identify the trajectory of that fireball event. Listen for any accompanying sound. So how does it sound like? Is it loud bang, soft bang, no bang? So how does it sound like? And record the timing, the time and the brightness of the fireball event. So is it bright? What kind of color was the light? This size and shape of the fireball. So all this information are really important for us when we study them, when we study fireball events, and also would help us locate the actual meteorite fall. So this is how we found the Winchcom meteorite, because of those video cameras recording where the meteorite fell from. So the fireball event, and that is what we used to finally locate the location where we should scout for the meteorite. So very important information for us to locate them. And when you find a meteorite, what you should do is, before you so excitedly pick it up, first first of all, take a photograph of it before you pick it up. Mark the location of it using your phone GPS. Just remember where it is from and the exact location. And usually when that happens, that there will be other pieces of meteorite that fall within the same region. So sometimes it's not just one of them. Sometimes within tens of meters apart, you might be able to find another one. So try to look for the second one. You might be lucky, super lucky that day. And you could use, remember the video I was showing you in Antarctica, people use aluminum foil to wrap it up. Use clean aluminum foil, not the one that you've baked some food in it, not that. Clean piece of aluminum foil. Wrap it up, put it in clean container to store it. Dry container to store it. No nylon, because nylon could cause some contamination to organic analysis. And finally, don't touch it with your hands. Don't touch it with a magnet. Basically, don't touch it with anything. Sorry, I'm blowing to the mic. Yeah, just because your hands got a fingerprint, you've got oil that will contaminate the meteorite, and we could trace it. We could trace that it's been picked up by someone because we've traced sweat, something like that, from meteorite, and that would overprint the organic content of the meteorite. So don't touch it. And with the magnets, because sometimes the magnetism of meteorite could tell us a lot. It could tell us where the things were came from, how they were formed, crucial information. So if you touch it with a magnet, it will erase all this information. So it's quite contradictory, because sometimes you need a magnet to tell, is it magnetic? Because sometimes things look like meteorite, but they're not. Sometimes we call that meteoron. So meteorons sometimes look like meteorite, but they do not stuck to magnets. So this is sometimes the way that some people use to identify meteorite. But then once you identify that it is a meteorite, at the same time you erase the history of it. So it's kind of like, is a gamble. So don't touch it with the magnet. So here, another activity for the chat section. Let me switch on my video as well. I've been doing all this gesture to my room. Thank you for pointing that out, Keith. Right, so here, which one is a meteorite? Which one is a meteoron? So please put in your chat box which one you think is a meteorite. The left one or the right one is the real meteorite. Left and right. Left. I got you. Right, so it's very challenging, isn't it? It's difficult because I just picked this to trick you. I just picked this image to trick you. The reason why we think the left one could look like meteorite is because of that look like fusion crust, doesn't it? It looks like the fusion crust is so dark, it's so glassy, it looks like it. But this is the one that also look like some terrestrial rock also look like this. Like the when you go to a iron mine, sometimes a mineral called hematite looks like exactly like this. So it's kind of that kind of fluster, that kind of shiny bit. It looks like a meteorite. But then this, when you've got that magnet and when you erase the information, there's no information for you to erase because it does not react to magnet. It doesn't contain as much of iron in the sample, so it's not a meteorite. And on the right, you could see all these chondrules. On Earth, you don't, when you look at rocks, when you look at them, sometimes you see crystals with irregular shapes. When you find chondrules, like circular blobs of crystal like this, like that there. Those are chondrules. So Earth rock doesn't contain chondrules. So when you see that, is pretty much telling you that yes, this is a meteorite. So meteorite, meteorome. Winchcom meteorite, a little bit of fusion crust you can see on the surface, a lot of chondrules you can see in the interior. So this is how people identify this as a meteorite. And there are several types of meteorite. So we mentioned about the iron-rich meteorite and not as iron-rich meteorite. So basically, they are separated into two different types: undifferentiated or differentiated meteorite. And there are different examples of that. So what that means, differentiated meteorite are just like our planet Earth. It has been differentiated into the Earth core, the mantle, and the crust layers. And that's because it, when it was like cluster of rock gets so big, it heats up in the middle, and then it becomes a core. And that cores, and then the entire thing grow bigger and bigger, becomes a planet. And when it gets so hot, it got completely molten. So that molten thing got slowly segregated into layers, and that becomes a planet. So that is the differentiation, planetary differentiation that we're talking about. So the interior, where we've got the core, becomes the iron meteorite. Here, it's composed of iron, it's super heavy. And then on the surface, on the crust, is what we call the achondrites. So they are more rocky bits, just like when you go outside and pick up a rock. That's sort of rocky type of material is called the achondrites. So, and the boundary between the core and the mantle gives you this amazing stony iron meteorite that composes of just 1% of all meteorite collected on Earth. So very rare, but super pretty kind of meteorites. And it tells you that it comes from a big body, just like a planet, and got segregated into different layers because it has once melted and got segregated in the layers. And example of a achondrite is the Martian meteorite. Again, the famous Ellen Hill 84001. It's famous because it's been talked a lot about whether people found microorganism inside of it, microbacteria. But so until today, most of the people find it difficult to completely convince them that what they're seeing this feature are micro bacteria. So they think it's just a mineral. So this is a Martian meteorite. Martian meteorites are part of achondrites. We haven't broken up the Mars into to access to the core to get the iron meteorite. So Martian meteorite mostly, all of them are achondrites. And then we've got my favorite kind of meteorite, undifferentiated meteorite. The difference between these two is that the undifferentiated meteorite has not been differentiated. They have not been melted since they were formed. So when they were formed, so the first bit of solid, as we mentioned, that were formed in this birth of our solar system, it is CAI, calcium aluminum rich inclusions, or the chondrules, right? So when the solid form, they kind of cluster together to form bigger and bigger pebbles, and then it grows bigger into a planet. But some material didn't get that big. It just keep it is a small size. It doesn't grow into a planet. And those never get melted. And those material are what are so exciting because they have not been melted. So information about the birth of a solar system is still contained within them. So it's got a lot of information that we could melt from these samples. So Winchcom meteorite, again, is a undifferentiated meteorite, unchanged, unmelted since the formation. Another example is the Murchison meteorite. It fell in 1969, the same year when we celebrated the return of the first lunar sample by Apollo 11. So we've got the laboratory set up for Apollo, and we've got the meteorite for, we've got the instrument ready just for that. So that's why a lot of organic analysis, a lot of understanding about the organic inventory at the birth of the solar system comes from the study of Murchison meteorite, fell in Murchison in Australia, 1969. So now we go to a step into my research realm is about the origin of life. So the reason why I study meteorite, because I'm interested in this point. And there are three theories to the origin of life. There is the theory that everything is earth-based. So the raw ingredients, the precursor molecules were all created on Earth. And it got more complex by growing into bigger molecules, more complex molecule into what we're seeing today, what we call life. So that everything is earth-based. That's one theory. The other theory, panspermia, you might have heard of it. It means that it's got life carried through the space rock from somewhere else, not from the Earth. So not just organic material, but life itself created somewhere, exists somewhere, and got carried to the Earth. So that is a different theory. And my kind of working on type of theory is the origin of life could be Earth-based because we've got life here, so it could be Earth-based, but the material, the raw material, could have come from somewhere else. So meteorite plays an important role. It brings the raw ingredient. It could be created anywhere in the solar system or in the universe, got carried by meteorites and arrived to the Earth, and complex reaction occur and then form life on Earth. So it could be either one of them, or it could be all of them that could have happened that caused the origin of life to take place. So this is my kind of favorite theory. And so now so this is a 24 hours of Earth's history. So the 4.56 billion years old of Earth. Just imagine that shrink into that 24 hours. So when we started about a minute ago, Homo sapiens came to the Earth about a minute ago. And then we've got dinosaur, all this origin of life going to simpler life form first. And the earliest life form that we found in the history of rock comes from what we call the stromatolite. It's algae kind of material, kind of organism. It's the oldest life record on Earth and in rocks, and also it still exists in nowadays. This kind of stromatolite still exists nowadays. And at about 2 a.m., that was a period of time when Earth was bombarded by space rock. So a lot of more than ever nowadays, so much more than nowadays, arrive on the Earth's surface at about 2 a.m. So that we know is a period where life could not exist, because that heavy bombardment period is just too hostile for life. And if life did exist before that, it would have been erased by that heavy bombardment period. So no life, no record of life before that. It would not be possible. And all this orangey color are when we know that we've got water on Earth, and when we know that we've got also life exist all the time in this orange section. So the tiny window there is the question mark, is the window into the origin of life. So the black bit is when we know there's no life could exist, and or if it exists, it wouldn't be on the record. And all the orange is we've got the record. So what happened at that point? That is the window of the origin of life. So this is the mysterious point that we study. So nowadays, when we talk about building blocks of life, when we talk about life, we always talk about associate that with water, lipids, carbohydrates, proteins, DNA. All these macromolecules are essential components of life. We know life must use them. They need them to exist. So these are the building blocks of life. We have not found them in meteorites. We have not found DNA. We have not found protein, lipids, but we have found the precursor of that. So protein, for example, made up of amino acid molecule linked up and form protein, a macromolecular structure protein. So protein we have not found, but the thing that made up protein, amino acids, have been found in meteorites. Carboxylic acid, sugar, amino acid, nucleobases. They are all found in meteorite. From the study of Murchison meteorite, other meteorite, we know that this molecule exists in this meteorite. And they're not coming from contamination. They were created before they arrived on the Earth's surface. So some reaction must have taken place in space that formed these molecules. And the meteorite is a messenger that carry them over here for complex reaction to further occur to create the first cell. So that's very interesting that we've got these molecules, but how were they formed on asteroids? In what condition can they form? Those are the questions that we try to answer when we study meteorites. So when you sometimes hear the news about, we found organic material in meteorite, what that means. Basically, it's anything to do with all these elements, hydrogen, oxygen, carbon, nitrogen, etc. So these elements form molecules, and together we call that organic molecules. And organic matter has got two different types in meteorites. So it's got mostly insoluble organic matter. So they have large cluster of those elements formed from cluster of macromolecule. It's got no direct correlation to life. It was formed by the same types of elements. And there are other types, what we call the soluble organics. They are soluble by common organic solvents in the lab or by water. Organic solvent like methanol, for example, can extract some of those organic molecules. Those are usually smaller, like amino acid. This is the size of it. So you could name those elements instead of like this macromolecular molecules, so many of them. Amino acids are smaller, but they are essential because, as we were saying, they form peptides and they form proteins at the end. So they've got more direct link to life. And all these organic molecules been found in meteorite. Don't worry, I'm not going to go into any of this in further details today, but we just know that we've got a lot of them, a lot of organic molecules, and they together form amino acids or sugar or nucleobases that form important organic molecules like protein and DNA. So when we study this precious meteorite, we work in the lab like that. Remember, I have to put on all the full gear. And these different clean labs are in different classifications. Class 1, 10, 100, basically how clean they are. The lunar sample, for example, the Apollo sample, stored in an ISO class 6 lab. So which means that per cubic feet, we've got only less than 7 of particles that are over 5 micron in size. So over 5 micron in size, you just got 7 particles sitting around in that space. So very clean space. And we use those space to study meteorites. So other than organic molecules, we've got water. That's another essential thing that we always talk about. And that links to what we call the snow line in our solar system. So this is our solar system here. We've got Earth there, we've got Jupiter. And between Earth, between Mars and Jupiter. That's the asteroidal belt. And this is where the water snow line is. And further away here, this is where the carbon dioxide snow line is. What that snow line tells us is that that molecule, so for example, water, could condense. So it no longer exists in a vapor form. It could condense into a condensed molecule instead of in the vapor form. So for example, an asteroid, if you sit further away from the sun of that snow line, you could contain water within you. So if you're sitting a bit closer to the sun from the snow line, you cannot contain water. So this is very important because that is a boundary setting where some asteroid could contain liquid water sometime in the past, or ice sometime in the past. So very important. And this material, where it's sitting further away from the sun, from the snow line, water snow line, could have been disturbed in this history. So for example, an asteroid called a C-type asteroid is a carbon-rich, water-rich kind of asteroid. Is sitting further away from the snow line. It will go maybe closer to Jupiter, got disturbed by its gravity, and then the orbit is no longer stable. So the disturbed orbit would carry that asteroid material closer to the Earth, and it might cross path the Earth, and that's probably how we got liquid water. Because otherwise, how could we got liquid water if we cannot hold it? We're not in a position to hold it because we're not at the snow line. So that's why it's very important that we study asteroids, because some of them carries liquid water within them. How was that liquid water like when they were formed? What's the role of that liquid water? Did it contain some complex molecule that yielded life? So that's quite exciting that we study liquid water in meteorites. But most of the meteorite, so far that we've studied meteorite, this is an Auguste meteorite, fell in France many years ago, 100 years ago, 1864. Auguste meteorite. It contained a lot of mineral that tells us that it's been in action with liquid water in the past. So it tells us indirectly that there was water on the asteroid in the past, but still indirect information. And this is not what I studied for Monahan and CAG meteorite. So these two meteorites are very, very special. So this is one of the paper that Keith mentioned about. Monahan and CAG meteorite fell in 1998 at two opposite places on the Earth. And one thing that they share in common is that they've got this blue colored salt crystals within them. It's not common. It's just we've found blue salt crystal within these two meteorites so far. Another so interesting thing about the blue crystal, salt crystal, is that they contain liquid water within them. So it's not the indirect evidence that we were talking about for Auguste, where you've got molecules, where you've got minerals that tells you that it has got action of water in the past. Not that. It's got liquid water within them. How do we know that? Because you could see a tiny air bubble inside of this fluid inclusion when you look at them under the microscope. So you see that vibration of that bubble is from the tiny movement of the microscope, and then some gears, some part of mechanic, or the little vibration from the desk, something like that will cause the little bubble to move around. It is not any form of water, but liquid water within this crystal. And so we study them with Raman spectroscopy and comparing the spectra to water spectra. We know that they match so well. They've got that band there. So it is not other kind of liquid. It is water and it's liquid form. So very, very exciting. So what I did, I took the revenge for dinosaurs. I crushed them. I crushed the meteorite. I dissolved that crystal, and I studied the organic material within them. A lot of different procedure in the lab. It could take a month if I'm super careful. It could be really a month to extract all these molecules out, chemically make them detectable by the machine, and study that with the machine. And we found amino acids, those that form protein. We found amino acid in salt crystal, the blue salt crystal. So the blue salt crystal hosting liquid water, it holds amino acids, the two raw ingredients that we need for life to take place. We've got it together in the same meteorite. They come from the same place. So what that place could be? It could be Ceres. It's one of the is a largest asteroid in the asteroid belt. It's a large that is even called a dwarf planet. So Ceres, we think that it could come from this, is one of the possibilities. It's carbonaceous rich material, and it's got this what they call the bright spot. It's a spot where they found salt and also surrounding some crater, they also found organics from that. And when we look at the mineralogy of Ceres and the mineralogy of the salt crystal, it contains some minerals within them. It matches quite well with what's reported for Ceres. So we think that, yeah, it could be one possible place where this that salt crystal come from, where the liquid water comes from, where the organic material comes from, including amino acids. Wherever that is, it has to be having a big body of liquid water for quite a long time, because when we study the isotopic composition, that's the conclusion that we made. It has to have this liquid water for a long period of time to give us that isotopic composition that we observed for the water and for the organics, for the salt crystal. So wherever it comes from, it's got this ingredient. It's got a large body of liquid water exist for a long time. What could happen? We will find out. So, so basically, this is it. The talk about what I study, and focusing more on the discovery of liquid water and organic material, and what that could tell us about where it was from, and what that could tell us a bit more about the origin of life. So, and I really want to share with you a bit more about what I do recently about the mission sample return, about the Hayabusa 2 samples, about Winchcom. We get to study the Winchcom meteorite for the organics as well. I would hope that there will be another chance where I could share with you all this exciting bit of research that I do. But today, I think times is about right, and I think we have to go to the Q&A section. So I'm now looking at the chat, and I'm still seeing left, right, left, right. So feel free to put down your question in the chat box, or just use your microphone and ask the question, and we could chat for a little bit before I take too long of your time for your next exciting activities that you've been organized for today. Well, thank you so much.
Well, thank you very much, Queenie, for an absolutely fascinating talk. I have to say that last part about where you can see the water moving in the salt crystal was just amazing. Just to give an idea of scale, while people are thinking of questions to ask, an idea of scale of that, the amount of water that was trapped in there, what sort of I'm imagining it's minuscule, but what's the scale of that?
Yeah, that's a really good question, because this is something that I really want to talk about, is the scale of things that I get to study in the lab. Because meteorites, they are big. You know, when people are on the news, when they say, okay, I've got a meteorite fell into my house, and they hold a massive meteorite. So sometimes people imagine that, okay, so we've got that much material for study. That's amazing. But most of the time, we got allocated a tiny piece of meteorite for study, because there were so many people around the world, so many qualified people, experienced people who could do so many different things, not just organic, you know, magnetic analysis, mineralogy analysis, etc. So sample allocation is very crucial, that people allocate just enough for your research and for the analysis. So for the meteoritic analysis, usually we get about milligrams of sample, and for organic analysis usually we need more of that, so I could get maybe a gram of sample, but that's it for meteoritic analysis, amino acid analysis. So we could get to take revenge of that 1 gram of stuff. So the salt crystal that you saw in those figures, the salt crystal, the entire blue crystal, is about 2 millimeter in size. And when we're talking about the fluid inclusion inside of them, they are even smaller. They are about 10 microns. So our hair, I've got kind of thick hair, but usually on average, people's hair's got a diameter of about 100 microns in size, 100 micron. And those fluid inclusion is 1/10 of it. So I cannot see it with my bare eye. I will have to use a microscope at quite a high power to take that image, to observe, you know, the air bubble and etc. So they're very tiny. And so 10 micron is about the kind of the average size of the fluid inclusion that we observed. We've got bigger ones, and we've got even smaller ones. So the smaller ones are really, really challenging to study. If they're sub-microns, smaller than 1 micron, we cannot really do much with them. But what we study there with the Raman instrument is try to see if it is water or other liquid. We then that was kind of bigger, is about 1/10 of the human hair. So these are quite challenging, but at least we could study them. Sometimes when I mentioned about, I study also dust particles, right? For example, the first Hayabusa mission that came to Earth quite some time back in 2014, 2014, sorry. It's carried dust particles that are about the same size of the human hair, or about half the size of the human hair. So I mentioned that you could barely see the particle with your bare eye if it's about 100 microns. So we need to pick up the particles with a needle instead of tweezer, instead of our hands. We would pick up by static electric a dust particle of that size to study. So those are another story that I would love to share with you in another talk. But this is the kind of scale that we were talking about when studying meteorites.
Well, I do actually have a question about small scale stuff again, but I'm noticing there's a couple of questions coming in on the chat. So I think it might be good if we cover them. I don't know if I believe John and Keith are keeping an eye on the questions coming in. So do either of you guys have you spotted a question for Queenie?
Yeah, there's one here. Do we have any specific chemical information about the Winchcom meteorite? Where any other fragments found? And that's from David Orr.
I would so much want to share with you this. So we've got the Winchcom meteorite fell in February. We collected the meteorite in March. because we've got so many observed fireball event of the Winchcom meteorite. We know, so we've got a team who calculated the orbit pre-atmosphere entry orbit of that meteorite based on fireball observation. So we know the orbit of it. We collected it the next day that it fell to Earth by a bunch of planetary scientists, people who knows how to contain clean in a clean, pristine environment of these space rocks. So it's almost like we're going to the orbit to collect that asteroid material to our lab to study. So we among ourselves we called it a tiny little UK space mission. A cheaper one too. We just pick it up from there. It's just a trip to Winchcom. So we've got the sample, and most of the time, initially we form what we call a UK Astronomical Study Group. So we've got different people, myself, Natural History Museum, Glasgow University, Manchester University, different planetary scientists. We form a group together. We know each other before. We know that they study different things in different universities, but this is the first time that we really sit together to work together as a team to study this rock that we treat it as a tiny little space mission. So we formed this team. We carefully segregate ourselves into different teams, and we are now in the process of getting the data, and we have some very exciting data already. And you could see that my lips, I try to zip up, and the zip is opening. So much that I wanted to share with you about the organic composition that we have just completed the analysis. Just let's see, I think it's 2 weeks ago. We just completed that. So we work with Imperial College, Kent University, Open University to study the organics of it. And there are other teams from Glasgow University, for example, study different parts, different focus of Winchcom meteorite. So we have now got the data, and we are now preparing to write the paper, and hopefully the reviewer will be kind to us and let us submit and publish it as soon as we can. But then we will have hopefully a lot of coverage on the news for to talk about. But something that we have been telling we've been doing initially about this Winchcom meteorite is that we classify it. So first thing is to classify what kind of meteorite it is. Is it a chondritic meteorite? Is it a carbon-rich meteorite? What? So we have found that it's a carbon-rich meteorite. It's very rare that we've got one meteorite fall into our soil, and also it is a rare carbon-rich meteorite that tells us so much about the organic composition, kind of my favorite, kind of thing. So we've got the classification information out about the. So when you ask about the chemical information, the thing that we know is that it is a carbonaceous meteorite, and this is one of those undifferentiated meteorite that has not been melted. So it's not been melted, representing the composition at the birth of our solar system, and it contained a lot of carbonaceous material, supposedly. So so this is something that initially we found, and then we're now looking closer into what kind of organics we've got in this meteorite, what kind of magnetic information that we've got, etc. So it's coming up pretty soon, hopefully, by the upcoming months. And I think we've got another question from John. Did you find out what gas was trapped in the bubble inside the pocket of liquid water, and how would it have been trapped there? So that's very interesting, because when we look at it, some of the bubbles they think is not gas, is vacuum bubble. So it's weird. I don't know how that could be possible, that you've got a vacuum bubble inside. But people think that during the formation, some of the gas could be trapped. That is to do with the temperature as well, what temperature that liquid water was trapped in. And sometimes when you trap in a kind of temperature, it reduces in temperature or expands in the temperature, the content inside of it, which is the liquid water, could change as well, and that could possibly form the vacuum bubble. And so this is what people are thinking about, that some of those are vacuum, because it is possibly representing that that there's a temperature change that caused the whatever formed inside shrink. So you've got some space created to form those bubbles. But most of the analysis so far with the water is the water content itself is already really challenging, because most of those analysis, especially isotopic analysis, you have to do directly on the sample. And if you've got the water trapped in a different kind of crystal, if it is not salt, if it contained oxygen in that, it will ruin the analysis, because when we do the analysis, we did so water, H2O, hydrogen and oxygen. So we do hydrogen isotopic analysis, oxygen isotopic analysis. If you've got a crystal, most of the silicate crystal contain oxygen. So that will cause some contamination to the analysis. So so it's very rare that we've got such a pristine water sample in the salt crystal that we could do such a high precision analysis on the water, hydrogen and oxygen. So that is already challenging. How do we expose that water out for analysis? And people use a frozen stage to keep the content frozen, so that when they expose the surface, they could then fire the laser of the ion beam onto it to study the content of it. So that is already very challenging. So far, we've been doing that. We've been doing organic analysis, for example. We've been dissolving the crystal to get the material trapped inside and see the mineralogy. And the next thing, probably we could find more, and hopefully we could then get to see what other organic molecules could we see, the more the wider range of it, and possibly even the composition of the vapor. Is it just vacuum, or does it compose of other kinds of gaseous material? Gordon, you're muted.
Yeah. After a year and a half of video calls, I still managed to do that frequently.
Yeah, I've been doing that for a couple of minutes for another talk that I haven't. They've heard my voice, but they haven't seen my PowerPoint presentation. They were only seeing me talking with those gesture. So therefore, I was telling you, reminds me if that happens as soon as you can, because I could go on forever without the PowerPoint talk.
Yeah, John and Keith, have you spotted any other questions coming in?
That's everything on the chat, I think.
Okay. Well, there's one just popped in from David Orr there. If you do observe a meteorite, who should you contact?
You could contact a couple of different people. So if you found a meteorite that you think could be a meteorite, you could contact the Natural History Museum. You could contact me, of course. You could contact Natural History Museum, and Glasgow University's got a couple of people who are studying meteorites too, and Manchester University as well, a couple of planetary scientists or meteoriticists who would be able to help identify the meteorite. There are some people who would be able to do chemical analysis, like private company with a prize, something like that. But I think you could contact, I think the best bit would be going to all these institutions and also Natural History Museum, because they've got quite a big range of instruments who will be able to do some analysis if they've got the time to confirm if this is a meteorite. But most of the time, if you could send the people some pictures, some high resolution pictures, focus on the interior of the sample to help to see if there is chondrule inside, etc. if they found chondrule inside, if they're more confident that it might be a meteorite, then they might be able to do some analysis for you. So, so all these universities, research institute, Open University is one of them. You will be able, you could contact them. But yeah, definitely you could contact me as well. If I don't know the answer, I could direct you to them as well.
Yeah, but following on from that, David, Caithness Astronomy Group have had a number of speakers in the past that have a definite interest in meteorites. So we have quite a few contacts. We've been lucky enough to have Caroline Smith from the Natural History Museum giving a talk in Caithness. And we've also more recently had Mike Sims, who's the curator over in the Belfast Museum. And he's a big, very keen on meteorites. In fact, there's a little story to do with the Winchcom meteorite. It actually fell just before the Caithness Science Festival last year.
Oh.
And Mike was extremely excited because he actually lived in the neighbouring village to where it fell. So he was desperate to get permission to travel from Northern Ireland across to check out the area and look for the meteorite. But it just so happened, as part of the Science Festival, he was giving a talk on space rocks and meteorites, essentially the day after the Winchcombe meteorite was found. So it couldn't have been better timing for it all to happen. It was almost like it had timed it so that it would increase the interest in space rocks, all just in time for his talk as part of the festival. But yeah, we do have a few contacts, David, if you or others come across them, and we now have another expert contact from Queenie who can advise us. So I think we're spoiled for choice now, which is great. Okay, I think there's a few other questions there. The best way to store a meteorite? Tin foil that you haven't used for cooking looks like a good option.
Yeah, the most important thing that so the most important thing about storage of meteorite is to keep it not wet, so keep it kind of dry environment. Although sometimes we recently realized that if you keep it in a really dry environment, you could suck the water out, and then things could recondense back on the surface, so you would get artifacts as well. But I think it's better still to keep it dry and free from terrestrial contamination, so in a storage box, and avoid touching it with fingerprint. Avoid using any organic substance around it. So the best bit, because sometimes even plastic box, that plastic itself is already, is already contamination, isn't it? So the best bit would be to wrap it in foil and then store in those containers. So in a cool environment, cool and dry environment, that would be the ideal place to store it in.
That's good advice there. I think there's been a few more coming in. I haven't kept track. John, have you been keeping an eye on?
Yeah, it's more to do with from Peter Sherman. He was asking, where is the best place or company to buy meteorites from? John McNichol has actually answered that there's a company or a shop in Edinburgh which you can purchase meteorites, and there's also Alan Toff, MS3 Meteorites, Martin Goff, UK. I don't know if you have anything to add to that, Queenie.
Yep, yeah, and I think I've got a so sometimes we even buy it from a dealer on eBay, but but you have to know the source of it. So if you're interested, send me an email so I could then forward to you those possible eBay dealers who is more trustworthy. Because when I was at Johnson Space Center, I did so Mike Zelensky, where I took the image with next to Big Lou. He is a curator at Johnson Space Center for the some space mission sample. So the Stardust mission went to the comet and got some samples back. So he was a curator of that. So he mentioned to me that sometimes they got the meteorites on private vendors like that too. But again, you have to know who to ask. So so if you're interested further in that, then definitely send me an email. Let's see if I could show you back to my screen, so you could copy my email address right here. So so you could ask me further in that sense. But yeah, but otherwise other companies that was suggested could be a possible source.
After we're finished your part of the session, one of the things that I will briefly mention is that you mentioned eBay, and I have a small selection of meteorite pieces that I got from reputable sellers on eBay, but there are quite a few reputable sellers in the UK and across the world. It really just depends on what you're looking for. So
Yeah.
I will mention a bit shortly about it, but my knowledge is limited on that front to who I've used. But if you're able to supply some suggestions, that would be great. What we can probably do is circulate it to our members as well, and then they have that information available.
That would link quite nicely with the next thing on your program for today, isn't it? How about owning your space rock?
Yeah. Well, there's a few topics that I'm going to cover at the end that I think link into obviously the meteorite side of it, space rock side, but also you're a planetary scientist, so there may be a few things there that link into some of the things that you know about. How are we doing for other questions? Is there any other ones that you've noticed coming up, John or Keith?
No, I think we're finished.
Okay, I have one more to add in then, and again it's going down to the tiny small scale of things. Right at the beginning you asked the question about how many elephants worth of space material lands, and it was 40,000 tons. And I remember reading somewhere that the majority of that is tiny dust particles, but there's lots of them. And I last year tried to collect some micrometeorites.
Oh, fantastic!
From the water runoff gutter from my roof. Now, what I did find is that there were lots of tiny spherical metallic looking things, but when I did a bit more research, there's in a town environment, most of them are likely to be earth made rather than falling from the sky, but there could well be some that are from space. Have you any tips or guidance on how I could tell the two apart? And I have to say, what you mentioned about picking things up with a needle through electrostatics, that's the kind of size that I'm finding. It is really about the size of a pinhead.
Right.
Have you any suggestions?
Yeah, so the micrometeorites are pretty small, but they in the small range, they are the slightly bigger ones. So they would be, so sometimes you could even pick them up with the pair of tweezers. So they could be slightly bigger. Have you also tried to use the magnet? Although I told you not to use the magnet to identify the meteorite, but usually when people sample micrometeorites, because from dust, from rooftop dust, from the gutter, it's just so many other dust. It's impossible that you go through them one by one. Sometimes there's just too many of them. So the only way for them would be to use a magnet to filter them out.
But
So that is
that's
one
what
way.
I did. I actually had a strong magnet attached to the underside of the gutter. So the flow of material ended up with a small pile stuck on the gutter where the magnet was, and then I could scoop that up and search through it with using a microscope.
Yeah.
But what I've found is there's lots of very tiny round metallic particles, but I wasn't. From what I'd read, it seems to be quite difficult to differentiate between the two just by visual. So if you've any guidance, that'd be useful, or if there's any better way to collect them.
Yeah. So I've got so the person who first amongst the first in the UK who sample rooftop dust is Matt Gensch at Imperial College, and so he so the method that you described, it was the method that they used initially to identify those microparticles. So sometimes on the surface of them, they will have some kind of molten features, kind of like, the kind of like the flow lines. So they've got some kind of that kind of feature that could be different from those other man-made particles. So a bit of that could give away some hints, but most of the time when we study them, we need to then look at the details to confirm if they are really micrometeorites. So we need to, mount them into a medium, polish it so that we could expose the interior to look at the interior. If it is just a bunch of, all this dusty earth man-made material, or if it's aggregates of tiny little crystals. So for next step that you could do is to look at the surface feature. I'm sure you have heard about you have read about the book, which images a lot of micrometeorites. Yeah. So that book could give away some hints of how the surface of the micrometeorite would look like, because they've been molten and recrystallized to form that shape sometimes. So that if you compare to that would give away the hints whether or not it's a micrometeorite. But then the next step would be to do more in-depth analysis. So I've got a summer internship who's working on it as well. She is about to collect some micrometeorite, hopefully, from our rain gauge as well. So if you're interested, then I'm sure she would be interested as well to speak with you and to exchange some ideas. So if you're interested, send an email to me to my email address, so that I could link you both up and share with each other some information. She's been working on micrometeorite for her master degree as well. So yeah, so send me an email so I could put you both in touch.
Okay, that sounds fantastic. Thanks. I'm not seeing any other questions, although there is an interesting comment just come in from John. Thanks for that. He said, don't use too big a magnet in your rainwater guttering, you might attract a very large meteorite. I think I could cope with a broken gutter if I could get myself a nice size sample. I do think the Winchcom meteorite that landed in the driveway, I wonder how happy the residents would have been if the car had been parked where it had landed. They may not have been quite so happy at the outcome. Okay.
That's right. Yeah, you don't want the large meteorite to block your drainage, don't you?
Oh, no. Now I've just got a wee thank you that I want to say, and to do that, it's easier if I share my screen. So hopefully, now, oh, come on, there we go. Now, we like to give our guest speakers a little something, and particularly something from Caithness. We're very keen in giving some Caithness gifts and produce and the like, and I'm delighted to say that we have somebody in Caithness who makes absolutely delicious chocolates, and we've got some chocolates and a few other things that we're going to send as a little token of our thank you for taking the time to give a talk, an absolutely fantastic talk for us tonight.
I want it.
And as part of that that little hamper of things that we're going to send, we thought, as you're a planetary scientist, you would appreciate a box of chocolates that are resembling the solar system. So you can see a photograph of what the sort of thing that they are like. This is courtesy of Caithness chocolates. The solar system's actually represented a little bit better these days. Apparently there's been some asteroids that have been added in as well. So it's not just the planets and the sun. There is a few asteroids thrown in for good measure. So I'm hoping that you'll enjoy them and the other things that we send to you in the post. It may take us a few weeks to get it all packaged up and send it to you, but you can look forward to a parcel arriving sometime reasonably soon. And I really want to say again, thank you very much for taking the time and for giving such an interesting talk. And perhaps we can manage to organise sometime in the future when you have some fascinating new news that you can give a talk for us again, whether it be online or if once all of the restrictions are lifted, if you felt that you were inclined to visit our end of the country, I'm sure we could arrange something along those lines as well.
Thank you so much. You're making it very difficult because they're so pretty. I don't know if I'm going to eat them.
Well,
I'm gonna just put them on a photo frame.
Well, you because they're freshly made, I think you've only got something like 3 months to eat them. So I'm sure you'll manage to work your way through it.
Thank you for having me, and yeah, definitely we'll get some more exciting data about the Winchcom and Hayabusa 2, and I'm sure you've got a long list of very exciting speakers coming up. But if you've got any spare time that we would like for me to come back, and I would absolutely love to. So just send me an email, let me know how things are going, and keep in touch.
Yeah, that would be fantastic. So now we're going to spend maybe 15-20 minutes with the other content. Feel free to remain connected and listen in, or if you need to go now and lie down, have a rest after giving the presentation and answering those questions, that's no problem as well. But you're more than welcome to remain connected as I run through the next 15 or so slides, and if you're still there at the end, we'll be having an informal chat with everybody that's left. So I'll leave it up to yourself what you want to do, but thank you once again for your time and giving that talk.
Thank you. I'm going to take a rain check of it because my pizza is waiting for me downstairs, my dinner. So I'm going to miss the yeah, so do keep in touch, and thank you again for this exciting discussion with the Astronomical group, and the exciting discussion, the lovely questions, and the lovely box of chocolate. I'm looking forward to it. Thank you so much.
Okay, well, thank you very much. And
take care. Good night.
Take care.
Bye-bye.
Bye-bye. Thank you very much.